Hello friends, welcome back. Today we'll learn about quadratic equations and expressions. So what exactly is a quadratic equation? So any equation of the form ax square plus bx plus c equal to 0, where a is not equal to 0 and abc are real numbers. Now this expression is called a quadratic equation in X. Now here ABC are real numbers. It's not necessary, but for our purpose we'll be learning only about the real number quadratic equation. You can always have equations in complex numbers also, right? So, but in this lecture we'll be learning only about ABC being real numbers. So now. The first concept which comes from a quadratic equation is the root of the quadratic equation. So any value of x which satisfies this equation, or say x is equal to 3 makes when you substitute x equal to 3, you get the left hand side equal to the right hand side, which is 0. Then you say that number as the root. So this is just indicative x is equal to 3 is and will not be the root every time. Okay. So let the root be alpha, or let's say the root is x itself. So this is the general way to find out the root. So for this quadratic equation, the root is given by the formula minus b plus or minus root of b square minus 4ac by 2a. Now you see there is a square root sign here. The term under the square root sign, b square minus 4ac, that is a very important term, and this is called the discriminant. Discriminant, sorry, it's not m, it's n. Oh, sorry. Okay. So this is discriminant. Okay. Now, clearly, if the discriminant, this is denoted by D, capital D. So if the discriminant is greater than 0, we say obviously the square root of that will exist, and hence we will get some real roots, right? But if the discriminant is not, so there are these three cases, right? First, if the discriminant is greater than 0, real and distinct. Real and distinct roots. If it is equal to 0, you will get real but same roots. And if it is less than 0, you will get complex or imaginary roots. Imaginary or complex. They both mean almost the same thing. They are not exactly same, but they mean almost same. Okay. So this is the basic condition for the nature of the roots. So the nature of the roots is directly related to the discriminant of the quadratic equation, which is given by b square minus 4ac. Fine. So let's say now a quadratic equation is nothing but a polynomial equation of degree 2. You can see, right, ax square. So x power 2. That tells us whether that is why this is called a quadratic equation. Now, a quadratic equation can have at most 2 roots, and let the roots be alpha and beta. So this is another very important property. Alpha plus beta, it is known as the sum of the roots. Sum of roots. Now this is given by minus b by a, and similarly product of the roots is given by c by a, right? So obviously here alpha, beta are roots of the equation. Okay. Now since alpha and beta are the roots of the equation, we know that alpha is the root if x minus alpha divides our quadratic equation ax square plus bx plus c. Similarly, x minus beta also divides the same equation, right? Hence, ax square plus bx plus c can be written as a into x minus alpha into x minus beta, right? Where alpha and beta are the roots of the equation. Now, I said a quadratic equation can have at most two roots, right? But what if there is an equation where you know that there are at least three roots which satisfy that equation? In that case, it's no more a quadratic equation; it becomes an identity, and in that case, a equal to b equal to c equal to 0, right? When more than two roots exist for the quadratic equation. Right? Okay, so whenever there are more than two roots for a quadratic equation, that means the quadratic equation actually doesn't exist, or it's an identity where a is equal to b equal to c equal to 0. Fine. So let us now look at a few other properties of the roots. So let's say our root is not a real number but a complex number, and let the root be p plus iq. Now what do we see about the now let's say the other root is beta, right? So sum of the roots is p plus iq plus beta, which is equal to, now it's given by minus b by a, right? We learned it just a few slides ago. So now we see that the complex part on the left hand side is iq, whereas on the right hand side there is no complex part. That means beta must negate this complex part, or in other terms, beta must be equal to p minus iq. How we get p here? That you will see, because p plus the product of the roots is p plus iq minus p minus iq. This will give us just p square plus q square, right? If you have anything instead of this p here, there will be some imaginary part in the product of the roots, which we cannot have since this is equal to c by a, right? Hence, if p plus iq is one of the roots, then the other root must be p minus iq. Right? So once suppose you have a question where one of the roots is given and it has some imaginary part, then the other root is directly achieved. Right? Similarly, if a quadratic equation is given where you see that all the coefficients a, b and c, all of them are rational numbers, then and if one of the roots is given as p plus root q, this is a real number, the other root is directly found out to be p minus root q. This is the second root. Now let's look for the condition of common root. This is a very common question in exams. Okay, so we have two equations here, ax square plus bx plus c equal to 0, and we have the second equation dx square plus ex plus f equal to 0, right? These are two different equations. Now let's say both of them share a root, or both of them have say alpha as the common root. So the question could be to find out the relation between ABC and DE and F, or some other condition provided ABC and these values are given. So what we are supposed to do in this kind of question is, let's say alpha is the common root, so you can obviously write a alpha square plus b alpha plus c equal to 0. At the same time, you can also write d alpha square plus e alpha plus f equal to 0. There is no point in writing the equation for the other root because that is not common and you cannot relate the two equations, right? Now what you do is, first, this is the first step, writing in this way. Second is eliminate alpha square from the two equations, right? Now there are a lot of ways to do that. I'm sure you all know that. Oh, sorry, from the two equations, not the second equation. Okay. So what you can do is multiply the first equation by d, multiply the second equation by a, and then subtract both of them. So alpha square is eliminated, and you have now you have an expression only in terms of alpha, which you can relate and find alpha in terms of b, c, e, and f. Similarly, next step is eliminate alpha from the equations. Right? Again, follow the same procedure. Multiply the first equation with e and the second equation with b, and then subtract the equations. So alpha term is out. You have only alpha square. Now you whatever you get for alpha, that expression squared gives you, should match the expression for alpha square, right? So that's how you will get the condition for the common roots. Now apart from this, so this is how you get the condition for one common root, right? Now what if both the roots are common? Now in that case it becomes very simple. For both common roots, this is the condition. It is very simple and it should come very intuitively also. C by f, right? So the coefficients should be in the same proportion. So if the equation I have is x square plus 2x plus 1 equal to 0, and if both the roots are common, then I should have say 4x square plus 8x plus 4 equal to 0. So you can see that in that case, a by b equal to b by e equal to c by f is equal to 1 by 4, right? So in that case, you will have any such equation, you will have the same roots, both the common roots, right? So that completes the condition for common roots. Now, generalizing these condition, generalizing what we learned for quadratic expressions for the polynomial ones. So we get polynomial expressions. I'll just go through some of the most basic results of polynomial expressions. Okay, so just like a quadratic equation or expression, this is the polynomial expression a x power n, a n minus 1, x power n minus 1, a1x plus a0 equal to 0. This is a polynomial equation. The expression is just still when you remove the equal to 0 part. So this will be the polynomial expression, right? So let's write this as f of x. So for f of x is equal to 0. Now this will have as at most n real roots, right? And moreover, we always assume that the coefficient of the leading term x power n, a n, should not be 0. Otherwise, it becomes a polynomial expression in n minus 1, right? Not in the order n. So this is for an expression of order n. Now in this case, let's write the sum and product of roots. Obviously there are n roots, so we have more than just sum and product of roots. We will have things like sum of all roots, right? Sum of roots, which will be let's say, okay, well, let the roots be, since there are n roots, let the roots be alpha 1, alpha 2 till alpha n, right? So these are some of the most important results related to polynomial expressions. Sum of roots, it is nothing but alpha 1 plus alpha 2 till alpha n will be given by minus an minus 1 by an. Similarly, sum of product of two roots taken at a time that means this is, so I am supposed to take two roots at a time. So I take alpha 1 and alpha 2 and I have to take all such combinations and add them up. So I have alpha 1, alpha 2, similarly I have alpha 1, alpha 3, I have like this, I have say alpha r, alpha j, which r and j obviously lie between 1 to n, till the last one is alpha n minus 1, alpha n. Now this is equal to, this is not alpha, this is a n minus 2 a n, right? So you take all the possible combinations of the roots to of the product of two roots and add them up. That should be equal to a n minus 2 by a n. Similarly, sum of product of r roots taken at a time, right? So this will be equal to say alpha 1, alpha 2 till alpha r. Similarly, alpha 1, alpha 2, instead of alpha r, I take alpha r plus 1 this time. Okay, like this, you will have a lot of combinations where you are taking r roots, product of r roots, and taking all possible combinations. This will be equal to, now this is the part which is important, minus 1 power r a n minus 1 by a n. Right. So we can see how we got this relation. So let's put it for r equal to 1. So you see that minus 1 power r is minus 1, and hence you get this minus sign. Similarly for 2, you put minus 1 power 2 is 1, so you got the positive sign. And actually putting n equal to 2, we can find this relation for, or verify the relation we obtained in quadratic equations. Okay. So similarly, the last one here is product of all n roots, and that is obtained by minus 1 power n, a0. This should be a0 by an. Right? So this was the part for polynomial expressions. Now there is one very important formula, one of the most fundamental formulae in quadratic equations or polynomial expressions. That is the remainder theorem. I just state the remainder theorem. We all know what it is, but just stating it is important. So the remainder theorem states that if x minus alpha divides f of x, then the remainder you get is f of alpha, right? Okay, so let's say I have a quadratic equation f of x, which is suppose ax square plus bx plus c, and suppose I divide f of x by x minus alpha, then the remainder I should get is nothing but f of alpha, or it is f of a alpha square plus b alpha plus c. Now the most important result from this is that suppose f of alpha is 0, right? Suppose f of alpha is equal to 0, then you get nothing that x minus alpha is the factor. or in other terms, alpha is the root of the equation, right? So this is the result from the remainder theorem. So the remainder theorem states that if x minus alpha divides f of x, then the remainder you get is f of alpha, and in case f of alpha is 0, then x minus alpha is the factor or alpha is the root. Okay, so now let's go back to quadratic expression and let's analyze it. So f of x is our quadratic expression, x square plus bx plus c. Now let's try to factorize this. Let's try to complete it. Let's try the computing by squares method. That gives us. So for that we take a common. Okay. Now I write this as x plus b by 2a whole square. Now let's expand this square. So we have x squared, and so this is accounted for. The next term is 2x into b by 2a, or b by a, bx by a. This is accounted for. But the next term is b squared by 4x squared, which is not there. Hence I must subtract that, and I get this. Taking the same denominator, I get this minus b plus minus b squared plus 4ac, right, by 4a squared. Now if you remember, b squared minus 4ac is nothing but the discriminant, or hence minus b squared plus 4ac must be negative of the discriminant, or this x plus b by 2a whole squared minus d by 4a squared. Okay, so this is our quadratic expression. Now let's try to see how the quadratic expression. Now this is nothing but a parabola. If you know, f of x is equal to ax squared, or f of x is equal to ax squared plus b is nothing but a parabola. And since a quadratic expression can be written in the form of a into x plus b minus 2 b by 2a whole squared minus d by 4a squared, hence this is also the same form, and this must represent a parabola. Now there are some cases from this, and let's see how we get this, arrive at those different cases. So let's take these, the different cases. So for the different cases, I'll first assume a to be greater than 0, right? Since a is greater than 0, that means the parabola must increase on both sides, right? So now once that is there, now let us take d negative. So if d is negative, I see that the minimum value it will take is, the minimum value is a into minus d by 4a squared, or minus d by 4a, right? So it must always. I'll just write the equation again here for reference. A times x plus b by 2a squared minus d by 4a squared. So this is the equation, and now consider a greater than 0 and b less than 0. Fine. So what do I get? So now since it is symmetric about x, and x equal to minus b by 2a will give us that will make the x square, the square part 0. That must give us the minimum one, and if a, and since a is greater than 0, minus b, making it positive, will be something like this. This is our x, and this is our f of x, right? This is okay. So this is our this line is not deleted at all. Fine. So the minimum point here is minus b by 2a, right? So minus b by 2a plus b by 2a whole squared gives us 0, and this point the minimum point is nothing but minus d by 4a. Since d is negative here, this must be positive, and so the implication is no real roots exist here, right? Now, this must be, this is nothing but a reminder, because we derived it earlier itself that d negative does not give us any real roots, but we just verified here graphically. Similarly, now I'll keep the same a, but now I make d equal to 0. So if d is 0, then the minimum possible value I get for f of x is nothing but 0. That is, however, at this point, it's something like this, right? Just touches it. So this is again the same point, minus d by 2a. However, since the root, so since the equation or the expression f of x touches the x-axis at one point, one root exists, and since there can be two roots, the same root is repeated. The root is x is equal to minus b by 2a. Okay, so now for the third one, what I do is I'll make d positive now, right? So we saw that our minimum value was nothing but minus d by 4a, right? Since a is positive, 4 is positive, and since now d is also positive, this whole thing becomes negative, right? So let's draw the graph again. Now, it should be below now. So what this means now is, my graph will have, since it has a minimum value, it will cut the x-axis at two different locations, and hence there must be two distinct roots. Two distinct roots, one on either side of the minimum value. So this is the minimum value somewhere here, and there are these two distinct roots. So let's now change a. Let a be negative now. Mind you, a can never be 0, otherwise this is not a quadratic expression, right? So now a is negative and d is again negative. So in this case, this will be just the mirror image of the first one. Why? Because you see, f of x is a times the whole parabola, right? So it depends on the directly on the sign of a. If a is positive, whatever be inside, if when you change a to negative, it will just become the negative of that, right? So this is the maximum value it can reach, again at minus b by 2a, but alas, there is no root, right? Similarly, for a negative and d equal to 0, so if this is the axis, I'll have this root, right? So there is only one root. And now for a negative and d positive, again the condition for real and distinct roots. So these are the two roots. So two roots. Okay. Now whenever I say roots, that means distinct roots, right? So two distinct roots exist here, because in the previous case one root means there are actually two roots, but the same root is repeated, right? So here two distinct roots exist. Okay, so that completes our all our basic results of quadratic expressions and equations in general, and polynomial expressions in quadratic equations in particular, and polynomial expressions in general. So in the next videos we will be looking at a few questions based on this and see how to use all these results. Thank you.